Imagine standing in a quiet room with a single light switch on the wall. The switch is currently in the down position. You know what that means. The light is off. If you lift the switch, the light will turn on. There are two stable outcomes: up or down, on or off. Now imagine that instead of touching the switch, you simply close your eyes and leave the room. You do not look. You do not interact. The switch remains physically in one definite position whether you see it or not. Your lack of knowledge does not change its state. It is either up or down the entire time. That feels obvious. Now, replace the switch with something much smaller. Not a device on a wall, but a tiny particle prepared in a laboratory. When measured, this particle also gives one of two outcomes. For example, a detector might click up or down. The result is always one or the other, never both at the same time. So the natural assumption forms quietly. Just like the switch, the particle must already be in one definite state before we look. Measurement simply reveals what was already there. But here is the question that begins to disturb that picture. If the particle already has a definite state, why do certain experiments behave as if it does not? If these are the kinds of questions you enjoy discovering calmly, consider liking the video and subscribing to the channel. It helps this channel reach others who appreciate slow explorations. And if you feel like it, share your thoughts in the comments. For now, let's return to this quiet room and this simple switch. Because with the switch, nothing changes when you turn away. Its state is fixed in space. But in quantum physics, when we prepare particles under controlled conditions and delay measurement, the outcomes follow patterns that cannot be explained by hidden pre-existing positions alone. Something about the tiny particle does not behave like the switch, and that difference is where superposition begins. Now picture returning to that room and deciding not just whether the switch is up or down, but changing the direction in which you examine it. Instead of asking up or down, imagine installing a new kind of device that tests the switch along a diagonal direction. In the ordinary world, that sounds meaningless. A switch does not possess diagonal states. It is mechanically constrained. It occupies one physical orientation in space. But with certain quantum particles, when we prepare them carefully and measure them along one direction, we may get up, measure again along that same direction, and we will reliably get up again. The result stabilizes. It behaves like the switch. Now change the direction of measurement, rotate the apparatus slightly. Suddenly the outcomes become uncertain again, sometimes up, sometimes down, with precise statistical patterns. If the particle truly had a definite hidden orientation all along, those rotated measurements should simply reveal a tilted version of the same fixed property, yet the numbers refuse to cooperate with that picture. The statistics depend on the angle between measurements in a smooth, continuous way. Notice what this means physically. The particle is not like the wall switch, which occupies a rigid orientation independent of how you look at it. Instead, its measurable property seems to depend on the very direction you choose to test. What physically exists before the measurement? There is a particle, there is a measuring device, there is an interaction waiting to occur, but the specific outcome is not settled in the way the switch's position is settled. The stable certainty only appears once the interaction happens along a chosen direction. That difference between a fixed mechanical state and something that responds differently depending on how it is probed is the first crack in the classical picture. And we have not yet named what fills that crack. Imagine insisting that the particle truly does carry definite answers for every possible measurement direction. You might picture it as holding a tiny internal compass needle pointing somewhere in space. Even if you do not know its direction, it must be there, fixed and waiting to be revealed. Now consider what that would require. If the particle carried a definite orientation, then for every possible angle at which you might measure it, the outcome would already be decided. The measuring device would merely uncover the stored answer. But experiments show something stricter than uncertainty. They show that no assignment of pre-existing definite values can reproduce the full pattern of correlations observed when particles are measured along different directions. This is not just about randomness, it is about incompatibility. When physicists attempt to build models where each particle secretly carries a full set of hidden instructions, one answer for every possible orientation, those models fail to match the actual statistics. What physically fails is the assumption that all properties can simultaneously possess definite values, independent of measurement context. The particle does not behave like a switch with a concealed position. It behaves as if the possible answers are not all written in advance. This is the crucial shift. Not uncertainty because we lack information, but structure that prevents all answers from existing at once. We have now removed the classical fallback, and what replaces it must be something fundamentally different from hidden rotation. Imagine preparing the particle again. Nothing changes in the setup. Same equipment, same conditions, same starting point. Before you measure it, what is actually there? We already know it is not secretly up, and it is not secretly down, and it does not carry a hidden arrow pointing somewhere in space, but something must be there, because when you measure it, the results follow a clear pattern. The numbers are not random noise. They change smoothly depending on how you turn the measuring device. That smooth pattern needs a cause, so instead of picturing a tiny object with a fixed direction, picture this. The particle carries a kind of readiness, a readiness to respond in different ways depending on how it is tested. Before measurement, it is not in one final answer. It is in a condition that contains several possible answers at once, not mixed in space, not half and half like paint, but held together as one single state. When you choose a direction to measure, that state produces one definite result. But before that interaction, it does not settle into just one. It holds multiple possibilities in a single description. That condition, where several outcomes are built into one state, is what we are slowly approaching. We just haven't named it yet. Imagine the particle just before the measurement happens. The device is set. The direction is chosen. The interaction has not yet occurred. What we have said so far is this. It is not secretly up. It is not secretly down, but it is also not empty. Something about it determines how likely each outcome is when the measurement happens. Let's make this more concrete. Picture standing at a fork in a path. Two roads stretch ahead. You have not taken either one yet. But the way the paths are shaped, their width, their slope, their direction, already influences how easily you might walk down one versus the other. You are not on either path yet. But the structure of the situation already shapes what can happen next. The particle is similar in this one specific way. Before measurement, it is not in one result, but it is in a condition that already contains the full structure of possible results and how strongly each can occur. When the measuring device interacts with it, the situation resolves into one clear outcome. But before that interaction, the description must include all the possible outcomes together, because those possibilities affect how future measurements behave. This is the key difference from the light switch. The switch is already in one position. We just might not know it. The particle is not already in one result. Its state truly includes more than one possibility at the same time, not as separate physical pieces, but as a single unified condition that contains several potential answers. And now we are ready to name this condition. That unified state, where multiple outcomes are present together before measurement, is called superposition. Not two particles, not two realities, one state, containing more than one possible result. Imagine now that instead of measuring the particle along just one direction, you build an experiment that allows two possible paths at once. Picture a small device that can send the particle left or right, depending on its internal state. If it were like the light switch, already fixed in one position, it would simply choose one path, left every time or right every time, depending on its hidden setting. But something different happens. When the particle is prepared in a superposition and sent into such a setup, the pattern that appears later on a detection screen cannot be explained, as if each particle simply chose one path in advance. If it had chosen left or right beforehand, the final pattern would just be a mixture of two simple results, like tossing pebbles through one opening or the other. Instead, the results show interference, regions where detections build up strongly, regions where they almost never appear. A striped pattern emerges, as if the two possible paths have influenced each other. Notice what this means. The two possibilities were not independent alternatives waiting to be selected. They were part of one single state that carried both possibilities together. And because they were carried together in one state, they could combine. This combination is not physical collision. The particle does not split into two smaller particles. There is still only one detection at the end. But before the measurement, the possibilities are not separate stories. They are components of one description, and those components can strengthen or cancel each other in predictable ways. That is something ordinary ignorance cannot produce. If the particle were simply secretly left or secretly right, no interference pattern would appear. You would only see a blended average. The appearance of interference tells us something precise. Before measurement, the particle does not travel one path or the other in the classical sense. Its state includes both possibilities at once, and those possibilities interact mathematically until a final outcome is produced. Superposition is not a lack of knowledge. It is a condition where multiple potential paths coexist within a single physical description, and their coexistence has measurable consequences. The screen continues to fill slowly with small points of light. Each detection is a single event. A quiet impact. One particle, one mark. Nothing about the individual impacts looks strange. Each arrival appears ordinary and localized. If you were watching in real time, you would see isolated flashes appearing at scattered positions. But over time, the scattered points organize themselves. Bright bands grow thicker, dark bands remain nearly empty. That emptiness is the key. If the particle had simply taken one path or the other in advance, the final pattern would be a simple blend of two distributions. Regions might be more populated than others, but no region would be systematically erased. Yet here, entire bands receive almost no detections at all. Absence appears with precision. This cannot be explained by saying the particle sometimes chooses left and sometimes right. Classical probabilities only add. They do not cancel. So something in the particle's description must allow contributions from the two possible paths to combine in a way that can either strengthen or suppress the final likelihood of arrival at a given location. Not suppress by blocking matter, suppress by reducing probability. Before detection, what exists is a single state that contains two path components. These components are not separate particles. They are not miniature objects traveling independently. They are parts of one unified description, and the rules governing that description allow these components to combine. In some regions, their combination increases the chance of detection. In other regions, Their combination reduces it nearly to zero. This combining happens before the particle is ever detected. Only once the particle interacts with the screen does one definite position appear. So superposition is not just multiple possible routes. It is a structured combination of those routes inside one state, and that internal structure shapes where outcomes can occur. That is forward motion, and it forces us to ask what exactly this structure consists of. Focus on one of the bright bands on the screen. Over time, more and more particles arrive there. The band becomes visibly denser than the surrounding areas. Now shift your attention to one of the dark regions. Particle after particle is sent through the apparatus, yet almost none arrive in that strip. Nothing physical blocks those dark regions. There's no wall in the way, no absorber. The space is open. A particle traveling like a tiny solid object should have some chance of landing there. But it does not. This tells us something precise about what exists before detection. The particle is described by something that behaves like a wave in one specific sense, not because it is literally a tiny water ripple, not because it spreads as a visible fluid, but because its description carries phase, and phase allows addition and cancellation. If two path components arrive at a location in step with each other, the likelihood increases. If they arrive out of step, the likelihood decreases. In some places, the reduction is nearly complete. So, before measurement, what exists is not a definite location and not a definite path. What exists is a state that assigns a kind of oscillating weight to every possible location where the particle could appear. That oscillation is not visible directly. You cannot see it traveling, but its effects become visible when many detection events accumulate. This is why superposition cannot be reduced to classical probability. Classical probability is always positive and simply adds. If there are two ways to reach a point, the chances stack. They never erase each other. Here, they can. That means the particle's state before measurement must contain more information than simple chances. It must include something that can interfere. Only after interaction with the detector does that structured state resolve into one definite position. Until then, the particle is not located at a single point. It is described by a spread-out structure of potential outcomes, and those potentials combine according to strict mathematical rules. This is not mystical. It is not about the particle being everywhere in a vague way. It is about the rules that govern how its possible behaviors are represented before interaction. Superposition is the name for that situation. One system, one state, containing multiple potential paths whose internal structure shapes measurable reality long before a single dot appears on the screen. And now we're close to identifying what that internal structure actually consists of. Two narrow openings are cut into a thin barrier. Behind the barrier is a detection screen. Particles are fired one at a time toward the two openings. This arrangement is known as the double slit experiment. If only one opening is left open, the pattern on the screen forms a smooth spread behind that slit. Open only the other slit, and a similar spread appears behind it. Now open both slits at the same time. If particles were tiny solid pellets choosing one slit or the other, the final pattern would simply be the sum of the two single slit spreads, a gentle blending of both shapes. But that is not what appears. Instead, bright and dark bands form across the screen. The pattern is not a simple addition. It contains regions where detections are nearly erased, and this happens even when particles are sent one by one with long pauses between them. Nothing physical connects one particle to the next. There is no crowding effect. Each particle travels alone. So the interference cannot be caused by particles colliding with each other. It must come from the internal structure of each particle's state before detection. Before it hits the screen, the particle is not described as having passed through only the left slit or only the right slit in a classical sense. Its state includes both possible paths as components of one unified description. Those components carry relative phase. That phase determines where reinforcement occurs and where cancellation occurs on the screen. Only when the particle interacts with the detector does one definite position appear. Until that interaction, the two path possibilities remain part of a single superposed state, and the double slit experiment shows something crucial. Superposition is not a philosophical claim. It is required to explain a measurable pattern that no classical mixture of hidden paths can reproduce. The dark bands are not decorative. They are the physical trace of superposition. Now place a small detector directly at one of the slits, not at the screen, not at the end, right at the opening itself. The purpose of this detector is simple. It answers one question. Did the particle pass through this slit or not? You send particles again, one at a time. If the detector clicks, you know the particle went through that slit. If it stays silent, you infer it went through the other. Nothing else about the setup changes. The distance to the screen is the same. The slits are the same width. The particles are prepared in the same way. But when you look at the screen now, something remarkable happens. The interference pattern disappears. The bright and dark bands vanish. In their place, you see the simple blended distribution you would expect if particles travelled through one slit or the other in a classical way. No cancellation, no precise empty stripes, just addition. What physically changed? The slits did not move. The screen did not move. The particles are the same. The only difference is that an interaction occurred at the slit that recorded path information. That interaction entangled the particle's state with the detector. The superposed components corresponding to left and right paths are no longer free to combine coherently. The internal structure that allowed cancellation has been disrupted. Before the slit detector was present, the particle's state included both paths in a way that allowed their phases to combine at the screen. Once the detector interacts with the particle, that delicate relationship between the path components is altered. The relative phase information becomes tied to the detector's state. As a result, the interference pattern cannot form. This tells us something very precise. Superposition is not about observation in the human sense. It is about physical interaction. When no path information is recorded anywhere in the environment, the superposed components remain coherent and can interfere. When path information becomes physically encoded, the coherence is lost. The particle does not change because someone looked. It changes because it interacted. Focus closely on what disappeared when the detector was placed at the slit. The slits were still open. The particle still travelled toward the screen. The screen still registered single impacts. What vanished was the interference. That tells us something extremely specific. The superposed paths were not destroyed by distance. They were not destroyed by motion. They were disrupted by information becoming physically available. When the detector at the slit interacts with the particle, even gently, it becomes correlated with the particle's path. If the particle goes left, the detector enters one state. If the particle goes right, it enters another. Now the total system is no longer just the particle. It is particle plus detector. Before this interaction, the particle's state contained two path components that could combine coherently at the screen. After the interaction, each path component is tied to a different detector state. Those detector states are physically distinct. They cannot overlap or cancel each other. As a result, the path components can no longer interfere when they reach the screen. Nothing mystical has happened. No conscious observer is required. What changed is that the particle's superposition became entangled with another system. Entanglement simply means that the description of one system can no longer be written independently of the other. The path information is now stored in the detector, and once that information exists in the environment, the coherence between the paths is effectively lost. This is why the interference pattern disappears. Superposition does not vanish because someone looks. It vanishes because the system interacts in a way that spreads path information into the surrounding world. And once that information spreads, the delicate phase relationship between the components cannot produce cancellation at the screen. So superposition survives only when the different possibilities remain physically indistinguishable. The moment the environment can tell them apart, even in principle, the interference fades. That principle will guide everything that follows. Now consider what it really means for two possibilities to remain physically indistinguishable. Before the slit detector was added, there was no trace anywhere in the environment that marked which path the particle had taken. No light scattered differently. No device changed state. Nothing in the surroundings carried a record of left or right. Because of that, the two path components remained part of a single coherent state. Their phases remained related in a precise way. That relationship allowed reinforcement in some regions of the screen and cancellation in others. The key word here is coherent. Coherence means the relative phase between components of a superposition is well defined and preserved. It is this preserved phase relationship that makes interference possible. Once the detector interacts with the particle, even slightly, the situation changes. The particle's path becomes correlated with a distinct state of the detector. That correlation spreads quickly. The detector may emit a tiny signal. That signal may disturb nearby atoms. Information ripples outward. Now the environment carries a physical imprint of the path. Even if no human ever reads the detector, the information exists. And once it exists, the relative phase between the path components can no longer produce interference in practice. This process is called decoherence. Decoherence does not select a particular outcome. It does not choose left or right. What it does is destroy the ability of the different components of the superposition to combine coherently. The superposition becomes entangled with countless degrees of freedom in the environment. When we ignore those environmental details, the particle appears to behave as if it has settled into one classical alternative. So superposition is not fragile because it is mystical. It is fragile because phase relationships are easily disrupted by interaction. To preserve superposition, a system must remain extremely isolated from its surroundings. Any uncontrolled interaction spreads information and erases interference. This explains why superposition is easily observed in carefully shielded microscopic systems, but almost never in everyday objects. The classical world emerges when coherence is lost, and that brings us closer to understanding what superposition truly is, not a paradox, but a precise structural feature of quantum states. Think about something much larger than a particle. Picture a grain of dust floating in a beam of sunlight. It drifts gently through the air. Now imagine trying to place that grain of dust into a superposition of two different positions, slightly separated in space. In principle, the equations of quantum physics allow it, but in practice, it would be almost impossible. Why? Because the dust grain is constantly interacting with its surroundings. Air molecules collide with it. Photons bounce off its surface. Thermal vibrations ripple through its structure. Each tiny interaction carries away information about where the grain is. Every collision becomes a kind of measurement, not a conscious measurement, a physical one. Each interaction entangles the dust grain's position with countless particles in the environment, and each entanglement spreads path information outward at incredible speed. The coherence that would be required to maintain a clean superposition of two separated positions is destroyed almost instantly, so the dust grain behaves classically, not because quantum rules stop applying, but because decoherence happens so quickly that any superposition becomes effectively unobservable. This explains something important. Superposition is not rare, it is universal. All physical systems are described by quantum states. But for large systems interacting with complex environments, the coherence between different components of those states vanishes extremely fast. The interference terms become practically inaccessible. What remains is a description that looks like a classical mixture, one alternative or the other, even though at the most fundamental level, the full quantum description still contains the larger entangled state. So the everyday world appears definite because information constantly leaks into the environment. Superposition is hidden by interaction, not removed from reality, just dispersed into correlations that are far too complex to track. And now we can see that superposition is not about particles behaving strangely. It is about how isolated a system is from the rest of the universe. Now follow that idea one step further. When a particle remains well isolated, its different possible states can remain coherent. That means the alternatives still carry phase information. The invisible timing relationship between them is preserved. Interference remains possible, but when the environment becomes involved, those phase relationships spread outward into countless degrees of freedom. Picture what that really means. A single electron passing through a double slit can maintain coherence because very little interacts with it, but replace that electron with something larger, say a molecule made of thousands of atoms, and the challenge increases. Every atom can vibrate. Every vibration can couple to radiation. Every coupling is a channel through which information leaks. The more internal structure a system has, the more pathways exist for coherence to disperse. Decoherence is not a force pushing something into one state. It is the loss of phase relationships between components of the wave function due to entanglement with the environment. That distinction matters. Nothing physically selects one branch in the fundamental equations. Instead, the branches stop interfering with each other because the information required to recombine them is no longer locally accessible. The mathematics still contains both, but operationally, each branch evolves independently. From the perspective of any observer embedded within one branch, the other becomes inaccessible. This gives rise to the appearance of definite outcomes, not because superposition vanishes, but because interference becomes practically impossible. The environment effectively monitors certain properties continuously. Position is especially vulnerable. Light scatters off objects. Air molecules collide. Thermal radiation interacts. All of this continually entangles spatial information with the surroundings. That is why macroscopic objects appear to have well-defined positions. Their positional superpositions decohere almost instantly. So what we call classical reality is not separate from quantum physics. It is quantum physics under conditions of overwhelming environmental entanglement. Superposition survives only where isolation protects coherence, and that tells us something subtle. The boundary between quantum and classical is not fixed by size alone. It is defined by interaction. Consider now what superposition really contains before any measurement or decoherence spreads information away. A quantum state is not a list of hidden answers. It is a structured combination of possibilities with precise numerical weights and phase relationships. Those phases are not decorative. They determine how alternatives combine when systems interact. Think back to the double slit pattern. Each point on the screen receives contributions from both paths. The brightness at that point depends on whether the waves from each path arrive in step or slightly out of step. When the timing aligns, the amplitudes reinforce. When they oppose, they cancel. This means the wave function is not describing ignorance. It is describing a physical rule for combining possibilities. Each alternative carries an amplitude. That amplitude has both magnitude and phase. The measurable probabilities emerge only after squaring the total combined amplitude. That squaring step matters. It hides the phase in ordinary measurement results. But before measurement, the phase controls how alternatives influence each other. So superposition is not two separate realities sitting side by side. It is a single state whose internal structure determines future behavior. When we measure, we do not reveal which branch was secretly real all along. We create an interaction that selects one outcome according to the probability distribution encoded in those amplitudes. And once decoherence has separated branches through environmental entanglement, those branches no longer influence each other. Interference requires coherence. Without coherence, superposition becomes observationally indistinguishable from classical uncertainty, but the underlying description remains unified. This is why quantum theory predicts phenomena that no classical probability model can reproduce. Classical uncertainty adds probabilities. Quantum superposition adds amplitudes first, then converts to probabilities. That ordering is the structural difference, and it is this structure that makes superposition both fragile and powerful. Fragile because phase relationships are easily disrupted. Powerful because when preserved, they allow interference patterns, entanglement correlations, and behaviors that cannot be decomposed into pre-existing definite states. So superposition is not made of substance. It is made of amplitude relationships, and those relationships govern how physical systems evolve before observation locks outcomes into place. Now stay with that idea of amplitudes combining before probabilities appear. There is a simple way to feel the difference without mathematics. In ordinary uncertainty, you imagine a coin hidden under a cup. It is either heads or tails. You just do not know which. When you lift the cup, you discover the pre-existing fact. The probabilities reflect your ignorance. In quantum superposition, the situation is structured differently. Before measurement, the system is not in one definite outcome with ignorance layered on top. Instead, it is in a state where the alternatives coexist as components of a single description. These components are capable of interfering because their amplitudes add together. If you try to treat them like hidden classical options, the predictions break. Experiments testing correlations between separated particles make this especially clear. When two particles are prepared together in a shared quantum state and then separated, measurements on them show correlations stronger than any model based on pre-written local instructions can produce. This is not because information travels faster than light in the usual sense. It is because the joint superposition encodes relationships that cannot be decomposed into independent, definite properties for each particle. The state belongs to the pair as a whole. Only when a measurement interaction occurs does one of the correlated outcomes become actual for each side. But until then, the system is described by a superposition that spans both particles simultaneously. This is called entanglement, and it is not an extra feature layered on top of superposition. It is what happens when superposition involves more than one system. The amplitudes do not simply attach to one object. They attach to combinations of outcomes across systems. So superposition scales. A single particle can be in a superposition of positions. Two particles can be in a superposition of joint configurations. In principle, an entire laboratory could be included in one vast superposition. The limitation is not the formalism. The limitation is coherence. Once environmental interactions distribute phase information outward, interference between large-scale alternatives becomes effectively impossible. But at the foundational level, the structure remains the same. Physical reality evolves as a superposition of amplitudes. Definite events emerge when interactions entangle those amplitudes with environments that no longer allow them to recombine. At this point, it helps to step back and ask something very simple. If superposition is the basic structure, why do we ever experience a single definite outcome? When you look at a detector, you do not see a blur of overlapping possibilities. You see one light flash, one mark, one event. From inside the theory, nothing mystical happens at that moment. A measurement is just a physical interaction that entangles the system with a much larger system. The particle interacts with a detector. The detector interacts with air molecules, with photons, with your eyes, with neural activity in your brain. Each step spreads correlations outward. Before the interaction, the particle might be in a superposition of two outcomes. After the interaction, the combined system is in a superposition of two larger branches. In one branch, the detector reads up and your brain registers up. In the other branch, the detector reads down and your brain registers down. Because of decoherence, these branches no longer interfere. Their phase relationships have been dispersed into the environment. From within either branch, the alternative is inaccessible. This is why experience feels definite. It is not that superposition collapses in a dramatic physical rupture. It is that once entanglement with a macroscopic environment occurs, the branches effectively separate. Each branch contains a consistent record of events. The mathematics does not select one and delete the others. It evolves the entire entangled structure forward. What changes is the practical impossibility of recombining those branches to observe interference again. So when we ask what superposition is made of, we can now answer more clearly. It is made of amplitudes attached to possible configurations of physical systems. Those amplitudes evolve smoothly according to quantum dynamics. When interactions occur, they spread into correlations. When correlations become too complex to reverse, definite experience emerges. Nothing extra is added at measurement. The same rules apply at every scale. Only the degree of isolation determines whether coherence survives long enough for interference to be visible. So now we can return to the original question with clearer ground beneath us. What is superposition according to quantum physics? It is not a particle being in two places in the casual sense. It is not a coin spinning in indecision. It is not hidden ignorance about a pre-existing fact. Superposition is the rule that the state of a physical system is described by amplitudes assigned to multiple possible configurations at once. Those amplitudes are not mere bookkeeping tools. They combine, they interfere, they evolve continuously. Before interaction, the system carries structured possibilities whose internal phase relationships determine how future interactions unfold. When you measure, you are not peeking behind a curtain to uncover a single hidden value. You are participating in an interaction that entangles the system with something larger. That entanglement spreads phase information into the environment. Coherence between alternatives becomes inaccessible. Interference stops. And what remains, from your perspective inside one branch of that entangled structure, is a single, definite outcome. The underlying description never switched frameworks. It was amplitudes all along. The classical world you experience is the appearance that arises when superpositions become entangled with environments too complex to reverse. So superposition is not made of matter in two places. It is made of mathematical structure that governs how physical possibilities combine before observation partitions them into separate experiential tracks. If you strip it down to plain language, you could say this: reality at small scales is not built from definite properties waiting to be uncovered. It is built from structured possibilities that only become definite through interaction. And that is the quiet shift, not mystery replacing clarity, but a deeper layer of structure beneath what feels obvious. The light switch on the wall really is either up or down, but the quantum system beneath it obeys rules that allow possibilities to coexist, interact, and only later solidify into the single path you remember experiencing. That is superposition. Let's now press gently on something that often lingers in the background. If superposition is the natural state of isolated systems, and measurement is just entanglement spreading outward, then what actually determines which outcome you experience? The theory gives probabilities. The squared amplitudes tell us how often each result appears across many identical trials. But in any single run, one specific outcome is registered. From inside the mathematics, there is no additional physical trigger inserted at that moment. The evolution of the wave function remains smooth and continuous. This has led to different interpretations. Some propose that collapse is a real physical process, an additional rule layered onto quantum dynamics that forces one outcome to occur. Others suggest that all branches continue to exist, but observers become correlated with only one branch and therefore experience a single result. Notice something important here. The experimental predictions do not change between these interpretations. All of them reproduce the same observable probabilities. The difference lies in how we describe what the mathematics means. This tells us something subtle about superposition itself. Superposition is part of the core predictive structure of quantum theory. Interpretation concerns what ontological story we attach to that structure. The amplitudes evolve the same way regardless. Decoherence happens regardless. Interference appears or disappears depending on coherence regardless. So when we ask what superposition is made of, we do not need to solve the interpretation question first. At minimum, it is the formal rule that physical states combine linearly. That linearity is what allows amplitudes to add and interfere. If you removed superposition from the equations, the entire structure of quantum predictions would collapse with it. So even if physicists debate how to narrate the deeper meaning, the operational role of superposition is fixed. It is the engine behind interference, entanglement, and quantum statistics, and nothing in experiment has yet required abandoning that engine. So whatever interpretation one prefers, superposition remains the structural backbone of quantum description. Hold in your mind a simple physical act. Picture narrowing a beam of light through a very thin slit. As the slit becomes narrower, the beam spreads out more on the other side. You can visualize this. The tighter the opening, the wider the fan of light that emerges. Now replace the light with a single particle, like an electron. If you try to confine that electron to a very small region in space, you are doing something physically similar to narrowing that slit. You are restricting where it can be. What exists physically in that situation? There is not a tiny dot pinned at one exact coordinate. Instead, there is a wave function sharply concentrated in one region. To build such a sharply peaked wave, many different wavelength components must combine. That combination is a superposition. Each wavelength corresponds to a different momentum. To construct a narrow spatial bump, you must add together many momentum components. They overlap. Their amplitudes combine in such a way that they reinforce at one location and cancel elsewhere. If you remove that mixture of momenta, the narrow bump disappears. So localization in space is not a single definite momentum hidden underneath. It is the result of superposing many momentum possibilities with carefully arranged phases. And the reverse is also true. If the particle has a very well-defined momentum, its wave function stretches out smoothly across space. It cannot be tightly localized. It becomes broad and extended. That spread is not measurement noise, it is structure. This is where the uncertainty principle quietly emerges. It is not an additional law slapped onto reality. It is a consequence of how superposition works when describing position and momentum. A sharp position requires many momentum components. A sharp momentum requires many position components. Superposition is doing the work. Even the electron bound inside an atom is not sitting at a fixed point. Its stable configuration is a standing wave, built from allowed superpositions shaped by the electric pull of the nucleus. Those standing waves define the atom's size and energy levels. Without superposition, there are no standing waves. Without standing waves, electrons would not settle into stable configurations. Atomic structure itself depends on this combining of possibilities. Superposition is not a rare laboratory curiosity. It is the mechanism by which matter maintains form. Stay with the atom for a moment, but look at it more slowly. Inside an atom, the electron is held by the electric attraction of the nucleus. Classically, you might imagine it orbiting like a planet, but that picture fails immediately. An orbiting charged particle would radiate energy and spiral inward. Instead, what physically stabilizes the electron is a standing wave. Picture a string fixed at both ends. Only certain vibration patterns are allowed. The wave must fit exactly between the boundaries. If it does not, it cancels itself out over time. Now translate that into the atomic scale. The electric pull of the nucleus creates a region in which the electron's wave function must satisfy precise boundary conditions. Only certain spatial patterns reinforce themselves consistently as time passes. All other patterns interfere destructively and disperse. Each allowed pattern is built from a superposition of many position components and many momentum components arranged so that the overall structure remains stable. That stability is not a frozen particle. It is continuous internal interference. The wave function is constantly evolving, but its shape persists because its components combine in a self-reinforcing way. These stable patterns correspond to discrete energy levels. Why discrete? Because only certain superpositions satisfy the requirement that the wave function remains self-consistent under the atom's electric field. Any slightly different combination fails to hold together. So quantized energy is not imposed artificially. It emerges from which superpositions are dynamically stable. If superposition did not exist, there would be no way to build these standing patterns. The electron would either collapse inward or drift outward without forming persistent structure. Atomic matter depends on the possibility of combining alternatives into stable wave patterns. And that means superposition is not just about measurement outcomes. It governs how systems endure through time. It determines which structures can exist at all. Without it, there are no atoms, no chemistry, no solid objects. Superposition is the mechanism that allows stability to arise from motion. It is not indecision. It is structured persistence built from overlapping possibilities. Picture a small electron gun aimed at a screen in a dark laboratory. The room is quiet. One electron is released at a time. Between the gun and the screen stand two narrow slits. You already know what happens if both slits are open and nothing watches which one the electron passes through. Over time, an interference pattern appears. Bright and dark bands slowly build up from many individual impacts. Now imagine placing a tiny detector near one slit, not blocking it, just quietly checking whether the electron passes there. The pattern changes. The bright and dark bands fade. The screen now shows two broad clusters instead of an interference pattern. What physically changed? The electron still left the gun. The slits are still there. The screen still records impacts. The difference is interaction. When the detector is active, the electron becomes entangled with it. The path information is no longer contained only in the electron's wave function. It spreads into the detector's internal states. That spread destroys the phase relationship between the two path components. Without preserved phase, the amplitudes from the two paths can no longer interfere. The interference pattern disappears not because the electron chose a path earlier, but because the conditions required for interference were removed. Superposition did not vanish, its coherence did. Now turn the detector off again. No one watches. No information about the path escapes into the environment. The interference pattern slowly returns. This is the quiet inevitability moment. If superposition were merely ignorance about a hidden path, then watching should not matter. The electron would have taken one slit or the other regardless. But the pattern tells you otherwise. The presence or absence of phase-preserving isolation determines what structure appears on the screen. When coherence is protected, amplitudes from both paths combine. When coherence is disturbed, the combination becomes impossible. Nothing mystical occurred. The electron did not decide differently. The rule is simple. Interference requires superposition with preserved phase. Measurement spreads phase information into the environment, and once that happens, interference cannot form. That is the structural collapse of the classical picture, not because something dramatic happened, but because adding states is physically real. Let everything compress into one final image. An electron approaches two slits. If it remains isolated, its state contains both paths as phase-related components. Those components evolve together and combine at the screen. The pattern that appears is shaped by how those components add. If the electron interacts with something that records path information, the phase link between those components spreads outward. The two possibilities no longer combine. They evolve separately within a larger entangled state. The screen reflects that change. Superposition is not about a particle being literally in two places in a classical sense. It is about the fact that physical states add, and that the relative phase between those added components determines what future interactions produce. When phase is preserved, interference appears. When phase is dispersed, classical outcomes emerge. That is the whole mechanism. Not spectacle, not paradox. Just linear structure shaping what can and cannot combine. And once you see that, the word superposition becomes simple. It is how nature adds before it reveals.